The exemption from ground fault protection for fire pumps found within Article 240 of the National Electrical Code, referred to as the NEC, is rooted in the critical need for unwavering reliability during emergency situations. Fire pumps are essential for fire suppression, and their continuous operation is paramount. Ground fault protection devices, while enhancing safety under normal circumstances, introduce a potential point of failure. A ground fault, even a transient one, could trigger the ground fault protection, leading to the fire pump being de-energized precisely when it is needed most. This risk outweighs the benefits of ground fault protection in this specific application. Ground fault protection devices are designed to detect and interrupt ground faults, which are unintentional electrical connections between a live conductor and ground. These devices are typically very sensitive, and they can sometimes trip due to transient events or minor insulation imperfections, a phenomenon known as nuisance tripping. In the context of a fire pump, a nuisance trip could be catastrophic, rendering the fire suppression system inoperable. The NEC does not permit operating fire pumps on solidly grounded systems without additional protective measures. Solidly grounded systems, characterized by a direct connection between the neutral point of the power source and ground, can experience high ground fault currents. These high currents can create dangerous conditions, including the risk of electrical shock and equipment damage. To mitigate these risks, the NEC mandates the use of an isolation transformer when a fire pump is connected to a solidly grounded system. An isolation transformer is a specialized transformer designed to provide electrical isolation between its primary and secondary windings. This isolation prevents ground faults on the secondary side, where the fire pump is connected, from affecting the primary side, which is connected to the main power source. In essence, the isolation transformer creates a separate, electrically isolated power system for the fire pump. This ensures that a ground fault on the fire pump circuit will not trip the main circuit breaker, allowing the fire pump to continue operating. The NEC also permits the operation of fire pumps on ungrounded or high impedance grounded systems without ground fault protection. Ungrounded systems do not have a direct connection to ground. In this type of system, a single ground fault will not cause a large current to flow because there is no return path for the current. However, a second ground fault on a different phase will create a phase-to-phase fault, which will result in a high current and trip the overcurrent protection. High impedance grounded systems use a resistor to limit the ground fault current. This limits the amount of fault current that can flow, reducing the risk of damage to equipment. In these systems, a single ground fault will cause a small current to flow through the resistor. This current is typically not large enough to trip the overcurrent protection, but it is large enough to be detected by a ground fault monitoring system. The ground fault monitoring system can then alarm or trip the circuit breaker. Because ungrounded and high impedance grounded systems inherently limit ground fault currents, they do not pose the same shock hazard as solidly grounded systems. Consequently, the NEC does not require ground fault protection for fire pumps operating on these types of systems. In summary, the NEC exemption from ground fault protection for fire pumps is carefully balanced against the need for reliability and the potential for nuisance tripping. Solidly grounded systems necessitate the use of an isolation transformer to provide electrical isolation and minimize shock hazards. Ungrounded and high impedance grounded systems, due to their inherent ground fault current limiting characteristics, do not require ground fault protection. To elaborate further on the different grounding systems and their implications for fire pump operation, let's delve into the specifics of each system. Solidly grounded systems, as previously mentioned, are characterized by a direct connection between the neutral point of the power source and ground. This connection provides a low impedance path for ground fault currents, resulting in high fault currents during a ground fault. The high fault currents in solidly grounded systems can cause significant damage to equipment, pose a serious shock hazard, and potentially lead to a fire. Therefore, ground fault protection is typically required in solidly grounded systems to quickly detect and interrupt ground faults. However, as discussed earlier, the NEC makes an exception for fire pumps provided an isolation transformer is used. The isolation transformer effectively isolates the fire pump circuit from the main power system, preventing ground faults on the fire pump side from tripping the main circuit breaker. The primary winding of the isolation transformer is connected to the solidly grounded system, while the secondary winding supplies power to the fire pump. The secondary winding is not grounded, creating an ungrounded system for the fire pump. In the event of a ground fault on the fire pump circuit, the fault current will be limited by the impedance of the transformer, reducing the risk of damage and shock. Ungrounded systems, in contrast to solidly grounded systems, do not have a direct connection to ground. This means that a single ground fault will not result in a high fault current. Instead, the fault current will be limited by the capacitance of the system to ground. The capacitance to ground is the inherent capacitance between the conductors and ground, which is present in all electrical systems. In an ungrounded system, a single ground fault will raise the voltage of the unfaulted phases to the full line-to-line voltage with respect to ground. This can stress the insulation of the equipment and cables. Additionally, a second ground fault on a different phase will create a phase-to-phase fault, which will result in a high current and trip the overcurrent protection. Ungrounded systems are sometimes used in applications where continuity of service is critical, such as in hospitals and industrial plants. In these applications, a ground fault monitoring system is typically used to detect the first ground fault. A ground fault monitoring system will alarm, allowing personnel to locate and repair the fault before a second fault occurs. High impedance grounded systems offer a compromise between solidly grounded and ungrounded systems. In this type of system, a resistor is inserted between the neutral point of the power source and ground. The resistor limits the ground fault current to a predetermined level, typically a few amps. This limited ground fault current reduces the risk of damage to equipment and shock hazard compared to solidly grounded systems. At the same time, the limited ground fault current is high enough to be detected by a ground fault monitoring system. The ground fault monitoring system will alarm when a ground fault occurs, allowing personnel to locate and repair the fault. High impedance grounded systems are often used in applications where both continuity of service and safety are important. They are commonly found in industrial plants, data centers, and hospitals. The selection of the appropriate grounding system for a fire pump depends on several factors, including the existing electrical infrastructure, the criticality of the fire pump operation, and the risk tolerance of the facility. Solidly grounded systems are generally the most common type of grounding system, but they require the use of an isolation transformer for fire pumps. Ungrounded systems offer the highest degree of continuity of service, but they can be more difficult to troubleshoot and may require specialized equipment. High impedance grounded systems provide a good balance between safety and continuity of service, but they require the use of a ground fault monitoring system. In addition to the grounding system, other factors that should be considered when designing a fire pump electrical system include the size of the conductors, the overcurrent protection devices, and the surge protection devices. The conductors must be sized to carry the full load current of the fire pump motor, plus any additional loads that may be connected to the same circuit. The overcurrent protection devices must be sized to protect the conductors and the fire pump motor from overloads and short circuits. Surge protection devices should be installed to protect the fire pump motor and other sensitive equipment from voltage surges caused by lightning or other events. Regular testing and maintenance of the fire pump electrical system are essential to ensure its reliability and safety. Testing should include checking the insulation resistance of the conductors, verifying the operation of the overcurrent protection devices, and inspecting the grounding connections. Maintenance should include cleaning the equipment, tightening connections, and replacing any worn or damaged components. By carefully considering all of these factors, it is possible to design and maintain a fire pump electrical system that is both reliable and safe. Now let's examine some specific scenarios and how the NEC requirements would apply. Scenario 1 involves an existing facility with a solidly grounded electrical system. The facility is installing a new fire pump. In this case, the NEC would require the use of an isolation transformer to provide electrical isolation between the solidly grounded system and the fire pump. The isolation transformer would prevent ground faults in the fire pump circuit from tripping the main circuit breaker, ensuring that the fire pump can continue to operate during a fire. Scenario 2 involves a new facility with the option to choose the grounding system. The facility decides to use an ungrounded system for the entire electrical system, including the fire pump. In this case, the NEC would not require ground fault protection for the fire pump. However, the facility would need to install a ground fault monitoring system to detect any ground faults that may occur. Scenario 3 involves an existing facility with a solidly grounded system. The facility wants to install a fire pump without using an isolation transformer. In this case, the facility would need to convert the existing system to either an ungrounded or high impedance grounded system. This would involve disconnecting the neutral point of the power source from ground and either leaving it ungrounded or inserting a resistor between the neutral point and ground. Converting an existing system to ungrounded or high impedance grounded can be a complex and expensive undertaking, so it is typically only done when an isolation transformer is not feasible. It's important to understand that the NEC is a minimum standard, and in some cases, it may be necessary to exceed the NEC requirements to ensure the safety and reliability of the fire pump system. For example, a facility may choose to install ground fault protection on a fire pump even if it is not required by the NEC. This may be done to provide an additional layer of protection against ground faults. Similarly, a facility may choose to use a higher quality isolation transformer than is required by the NEC. This may be done to improve the reliability of the isolation transformer and reduce the risk of failure. The decision to exceed the NEC requirements should be based on a careful assessment of the risks and benefits. Factors to consider include the criticality of the fire pump operation, the potential for damage from a ground fault, and the cost of the additional protection. It is also important to consult with a qualified electrical engineer to ensure that any additional protection measures are properly designed and installed. Furthermore, it is crucial to stay updated with the latest version of the NEC and any applicable local codes and regulations. Electrical codes are constantly evolving to reflect new technologies and safety concerns. Staying informed about these changes is essential to ensure that the fire pump electrical system meets the current standards. In addition to the technical aspects, it is also important to consider the administrative aspects of fire pump electrical systems. This includes ensuring that the system is properly documented, inspected, and maintained. Proper documentation should include detailed drawings of the electrical system, including the location of all components, the size of the conductors, and the settings of the overcurrent protection devices. Inspections should be conducted regularly to ensure that the system is in good working order and that there are no signs of damage or wear. Maintenance should be performed on a regular basis to keep the system in top condition. This includes cleaning the equipment, tightening connections, and replacing any worn or damaged components. By paying attention to both the technical and administrative aspects of fire pump electrical systems, it is possible to ensure that these systems are both reliable and safe. And finally, remember that working with electricity can be dangerous. Always follow proper safety procedures when working on or around electrical equipment. This includes wearing appropriate personal protective equipment, such as gloves and safety glasses, and energizing the equipment before working on it. If you are not qualified to work on electrical equipment, hire a qualified electrician. Fire pumps are critical components of fire protection systems, and their reliable operation is essential for protecting life and property. By understanding the NEC requirements for fire pump electrical systems and following proper safety procedures, it is possible to ensure that these systems are both reliable and safe. The information provided here is intended for general guidance only and should not be considered a substitute for professional advice. Always consult with a qualified electrical engineer or other professional for specific guidance on your project. And be sure to refer to the latest edition of the National Electrical Code and any applicable local codes and regulations. Ground fault protection is a critical safety feature in electrical systems, designed to minimize the risk of electrical shock and fire hazards. While the NEC provides an exemption for fire pumps under specific circumstances, it's crucial to understand the underlying principles and requirements to ensure the overall safety and reliability of the electrical system. The exemption is not a blanket waiver, but rather a carefully considered exception based on the unique operational demands of fire pumps. Understanding the different types of grounding systems, The role of isolation transformers and the importance of regular testing and maintenance are all essential for ensuring the safe and effective operation of fire pumps. Always prioritize safety and consult with qualified professionals to ensure compliance with all applicable codes and regulations. The decision to implement or forego ground fault protection for a fire pump should be a well-informed one, taking into account the specific characteristics of the electrical system, the criticality of the fire pump operation, and the potential risks involved.